As electricity demand starts climbing again in many parts of the world, an old technology is being reintroduced with a new sales pitch. The question is whether small modular reactors, or SMRs, could become the next power plants for data centers, industry, and a more electrified economy, or whether they will turn out to be an expensive distraction from options that are already cheaper and faster to deploy. The timing of this debate is not accidental. Governments are trying to cut emissions while also dealing with a more crowded energy agenda. Electric vehicles, heat pumps, industrial electrification, hydrogen production, and rapidly growing data center demand. At the same time, they still care about security of supply, grid stability, and reducing dependence on imported fossil fuels or geopolitically sensitive energy chains. In that setting, anything that promises reliable low-carbon power gets attention very quickly. That includes nuclear. Large conventional nuclear plants have long offered a clear attraction: high-availability electricity with low operational carbon emissions. But they also carry heavy baggage. In many countries, they are associated with very high capital costs, long construction times, repeated delays, financing risk, and persistent political controversy. So when advocates talk about SMRs, they are not just saying, let's build smaller reactors. The real claim is that nuclear could be reorganized as a different industrial model. This is the core novelty. SMRs are presented as factory prefabricated, standardized units that can be assembled on site, rather than giant bespoke megaprojects built almost from scratch every time. In theory, that changes everything. Instead of each nuclear station being a one-off engineering marathon, developers could manufacture many identical units, learn by repetition, tighten supply chains, reduce uncertainty, and lower project risk. But that promise comes with an important condition, and mainstream analysis is careful about it. The benefits depend on genuine serial production. A one-off modular reactor is unlikely to deliver the cost or schedule advantages that supporters advertise. If only a few are ever built, or if every project is redesigned for each country and each site, much of the industrial logic starts to weaken. It also matters to be clear about what SMR means, because it is not a single reactor. It is a family of designs. Some are closer to familiar light water reactors, basically more evolutionary versions of existing nuclear technology. Others are more advanced concepts using different coolants, different operating temperatures, or different fuel forms. That diversity is part of the appeal, but it also complicates comparisons. A promise made for one design cannot automatically be extended to all the others. So why are data centers part of this conversation? Because they want something the broader grid increasingly struggles to guarantee everywhere: predictable, round-the-clock power. Operators care about reliability, and many also want low-carbon electricity for climate targets. In weak grid regions, in places with high fossil import costs, or where power demand is surging faster than transmission can expand, a dedicated or nearby firm power source looks attractive. That is one reason interest in SMRs is rising alongside the AI boom, not just because AI is fashionable, but because large-scale computing pushes electricity demand toward continuous supply. Still, the possible role of SMRs goes beyond feeding server halls. Their smaller size could fit remote regions, islands, mining operations, military infrastructure, and former coal plant sites. Modularity could also allow capacity to be added in steps rather than through one massive build-out. And depending on the design, the product may not be electricity alone. Some concepts are promoted for district heating, industrial process heat, desalination, or hydrogen production. That matters because some sectors do not simply need more electrons. They need continuous high temperatures that wind and solar, by themselves, do not directly provide. The strongest argument in favor of SMRs is not that they are magically cheap, but that standardization might eventually improve timelines, financing, and risk compared with custom-built conventional nuclear plants. Investors and utilities tend to dislike projects where every plant is effectively a prototype in cost and schedule terms. If a reactor model can be licensed, manufactured, and repeated many times with fewer surprises, supporters argue that nuclear starts to look less like a mega-project gamble and more like an industrial product. Critics respond with an equally important reminder: smaller does not automatically mean cheaper. A reactor still needs safety systems, trained staff, permits, grid connections or other infrastructure, and long-term institutional support. Some costs do not shrink in proportion to output. So while a single SMR may require less capital than a giant reactor, the electricity it produces is not guaranteed to be cheaper. Viability depends on supply chains, regulation, financing conditions, and political continuity. Without those, modularity alone may not rescue the economics. This is why the current wave of enthusiasm needs some discipline. There is no mainstream case here for a quick shortcut. Even in optimistic readings, SMR deployment looks gradual rather than sudden. It would require approvals, demonstration projects, industrial learning, customer confidence, and public trust. That is a long process, especially in a sector where delays are expensive and credibility matters. Safety is another major part of the pitch. Many SMR designs emphasize passive safety features. In simple terms, they aim to rely more on gravity, natural convection, or heat conduction, and less on active intervention. Smaller cores and different geometries may also improve heat removal in some designs. Supporters argue that this can reduce the probability or severity of certain failure scenarios. But improved safety claims do not eliminate risk. Open concerns remain around material aging, human error, cybersecurity, natural hazards, and the challenge of maintaining strong safety culture across multiple units. Emergency planning still matters. Oversight still matters. A more elegant design does not replace competent institutions. That is especially important if many units are deployed across different regions under uneven regulatory capacity. Waste is often discussed in overly simple ways, and the brief balance here matters. SMRs do not eliminate nuclear waste. Waste outcomes may vary by design and fuel cycle, but highly radioactive waste still requires long-term management. So blanket optimism is misleading. At the same time, blanket pessimism can also flatten real differences between reactor types and fuel strategies. The honest position is that waste remains a serious governance issue, not a solved problem, and not a reason to stop thinking carefully. The same applies to proliferation and international governance. Some advanced reactor concepts require special attention because of the materials or fuel pathways involved. International safeguards, controls, and transparent oversight remain essential. Technology alone cannot guarantee peaceful use. Any serious SMR expansion would still depend on institutions, monitoring, and trust between states. Then, there is the social and political reality. In some regions, placing SMRs at former coal plant sites is seen as a way to preserve local energy roles, existing grid connections, and some jobs. That can be politically attractive. But it is not a simple one-for-one swap. Skills, timelines, regulation, community acceptance, and economics all matter. And public acceptance varies sharply by country and political culture. In energy policy, technical viability and political viability are never the same thing. So, will reactors become the new power plants for data centers? The careful answer is, possibly in some cases, but not at the speed implied by the loudest headlines. SMRs could become a meaningful building block in the energy transition if they truly deliver standardized, compact, potentially faster, and more flexible nuclear infrastructure. They may appeal where reliable low-carbon supply is especially valuable and where alternatives are constrained. But critics are right to warn that they could also become a costly detour if the industry fails to achieve serial production, workable regulation, credible finance, and real-world delivery. In that sense, the next decade looks less like a breakthrough moment than a decision phase. The fate of SMRs will not be settled by concept art, press releases, or AI-era excitement. It will hinge on whether first projects are actually built on time, within cost, through workable approvals, with functioning supply chains and genuine customer contracts. That is the test that matters. Subscribe, enable notifications, and tell us in the comments which energy topic we should explore next.